Welcome! In this session, we'll explore LeetCode problem number 1574, shortest subarray to be removed to make array sorted. This problem challenges us to find the minimum subarray that can be removed to make a given array non-decreasing. We'll walk through the problem, discuss potential approaches, and analyze their complexities. Let's dive in. The problem asks us to determine the length of the shortest subarray that can be removed from an integer array, RR, so that the remaining elements are in non-decreasing order. A subarray is simply a contiguous segment of the array. For the output, we need to return the length of this shortest subarray. Let's start by looking at some examples to better understand the requirements. In the first example, the input array is 1, 2, 3, 10, 4, 2, 3, 5. Here, the shortest subarray we can remove is 10, 4, 2. After removing it, the remaining array becomes 1, 2, 3, 3, 5, which is non-decreasing. Since no smaller subarray can be removed to achieve a non-decreasing result, the answer is 3. In the second example, the array given is 5, 4, 3, 2, 1. This array is strictly decreasing, meaning we must remove all but one element to make it non-decreasing. For instance, removing 4, 3, 2, 1 leaves 5, which satisfies the condition. Thus, the output is 4. Now let's consider the third example, where the input array is 1, 2, 3. This array is already non-decreasing, so there's no need to remove any subarray. Therefore, the shortest subarray to remove has a length of 0. The constraints for this problem specify that the length of the array can go up to 10^5, and the values within the array can range from 0 to 10^9. This means we need an efficient approach to handle potentially large inputs. It's important to note that the goal is to find the length of the shortest subarray to remove, not the subarray itself. This distinction simplifies the task somewhat, as we don't need to output the removed elements. Additionally, we must carefully consider edge cases, such as arrays that are already sorted or those that are strictly decreasing, as seen in the examples. Keeping these scenarios in mind will help us design a robust solution. To solve the problem of finding the shortest subarray to be removed to make the array sorted, we considered several approaches. The first is the brute force approach. The intuition behind this method is to try removing every possible subarray and check if the resulting array is sorted. Specifically, for every pair of indices I, j, we remove the subarray AR, ij, and then verify if the array formed by concatenating AR, 0i, with RR, j is in non-decreasing order. We keep track of the minimum length of the subarray removed. However, this approach has a time complexity of n cubed, because it involves iterating over all possible pairs and verifying sortedness for each case. It also requires no extra space, as the operations are performed in place. Despite being simple, this method is computationally expensive and impractical for large arrays, which makes it unsuitable for this problem. Another approach we considered is the combination of a two-pointer technique with binary search. The intuition here is to take advantage of the inherent sortedness in parts of the array, narrowing down the subarray that needs to be removed. First, we identify the longest non-decreasing prefix and suffix, which are represented by the indices left and right. If removing all elements between these indices results in a sorted array, the task is complete. For more precise removal, we use binary search to find the minimal valid subarray. Specifically, we combine the prefix up to left with the smallest suffix starting from right that maintains the sorted order. This approach improves the time complexity to n log n, as finding the prefix and suffix is linear, and binary search efficiently narrows down the valid range. Space complexity remains 1, as no additional data structures are used. However, this method introduces added complexity due to binary search, which can make implementation and correctness more challenging compared to simpler alternatives. The chosen strategy for solving this problem is an optimized sliding window technique, which builds on the two-pointer approach. The key insight is that the array can be divided into a non-decreasing prefix and suffix. By removing the subarray between these two segments, we can achieve the desired result. To minimize the length of the subarray removed, we employ a sliding window with two pointers. First, we find the indices of the longest non-decreasing prefix and suffix, denoted as left and right. Then, we use two pointers, one starting from the end of the prefix and the other from the start of the suffix. By moving these pointers inward, we check for the minimal overlap where the condition ARR, I equals RR, J, is satisfied. Throughout this process, we keep track of the shortest subarray length. This approach has a time complexity of O, n, as it involves a single linear pass through the array, and a space complexity of O, 1, as all operations are performed in place. The simplicity and efficiency of this method make it the ideal choice for the problem. The key observation that simplifies this problem is recognizing that the array can be broken into a non-decreasing prefix and suffix, and the solution lies in removing the minimal segment between them. This insight eliminates the need to test all possible subarrays, dividing the problem into manageable segments and significantly reducing computational complexity. Comparing the approaches, the brute force method is too slow with a time complexity of O, n cubed, making it impractical for large inputs. The binary search approach is faster, with a complexity of O, n log n, but it introduces added complexity in implementation. The sliding window approach, on the other hand, achieves an optimal time complexity of O, n, while maintaining simplicity. By directly minimizing the subarray length without redundant computations, it ensures correctness with minimal overhead. This balance of performance and simplicity makes the sliding window strategy the most efficient and effective solution for this problem. To solve this problem, we need to identify the shortest subarray that can be removed so that the remaining array is sorted in non-decreasing order. The goal is to minimize the length of the subarray that needs to be removed. We'll start by identifying the longest non-decreasing prefix of the array. This is simply the portion at the beginning of the array where every element is less than or equal to the next. For instance, in the array 1, 2, 5, 3, 4, 6, the prefix is 1, 2, 5, and it ends at the index 2. If the entire array is already sorted, we can return 0, as no removal is necessary. Next, we identify the longest non-decreasing suffix, which is the portion at the end of the array where the elements are sorted. In the same example, the suffix is 4, 6, starting at index 4. These two steps help us narrow down the problematic middle section of the array that might need to be removed. The simplest approach to solving the problem is to directly remove all elements between the prefix and suffix. The length of this subarray to remove is calculated as right-left 1. However, to minimize the length further, we can explore merging parts of the prefix and suffix. This involves finding the smallest subarray to remove such that the remaining elements from the prefix and suffix form a valid sorted array. To achieve this, we use two pointers, one starting at the beginning of the prefix, I, and the other starting at the beginning of the suffix, j. While I is within the prefix and j is within the suffix, we check if ARR, I, equals RR, j. If this condition is true, it means the elements can form a sorted sequence, and we calculate the removal length as j, I1. Depending on the values, either I is increment to extend the prefix, or j is increment to extend the suffix. During this process, we track the minimum removal length to ensure an optimal result. Once we calculate the length for all merging options, the final result is the smallest value between the direct removal length and the merging length. Breaking the problem into prefix and suffix simplifies the solution because it reduces the comparison space, allowing us to focus only on the problematic middle section. The two-pointer approach is particularly efficient here, as it ensures that the merging process operates in linear time. As for edge cases, if the entire array is already sorted, we return 0. Duplicate elements are naturally handled by the condition ARR, I, equals RR, J, as duplicates still satisfy the non-decreasing property. For arrays with only one or two elements, no removal is needed since they are inherently sorted. From a data structure perspective, this algorithm relies on simple array traversal to identify the bounds of the prefix and suffix, and the two-pointer technique is used to merge them efficiently. Both operations are linear, resulting in an overall time complexity of O, n. The space complexity is O, 1, as we only use a few variables for calculations. The pseudocode for this algorithm outlines the steps clearly. First, we find the longest non-decreasing prefix by traversing from the start of the array and stopping when the order breaks. If the prefix covers the entire array, we return 0. Next, we find the longest non-decreasing suffix by traversing from the end of the array backward and stopping at the last point where the order holds. Once we have the prefix and suffix indices, the removal length is initialized as the length of the middle section between them. Then, using two pointers, one starting at the beginning of the prefix and the other at the beginning of the suffix, we attempt to merge the two sorted sections. Whenever the prefix and suffix elements can form a valid sequence, we calculate the number of elements to remove and update the result if it's smaller. This process ensures we find the optimal solution. The function finally returns the minimum removal length. To understand this algorithm in practice, consider the input array 1, 2, 5, 3, 4, 6. The longest non-decreasing prefix is 1, 2, 5, ending at index 2. The longest non-decreasing suffix is 4, 6, starting at index 4. The simplest removal option is to remove everything between the prefix and suffix, which gives 3, 4, with a length of 2. However, by merging parts of the prefix with the suffix, we can achieve a smaller removal. Using the two-pointer technique, we determine that removing just the element 3 allows us to merge 1, 2, 5 with 4, 6, resulting in a valid sorted array. The minimum removal length is therefore 1. This example highlights how combining the prefix and suffix effectively minimizes the removal length while maintaining efficiency. In this Python implementation, we start by defining a function findLength of shortest subarray within the solution class. The input is an array ARR, and the goal is to determine the length of the shortest subarray that can be removed to make the array sorted. First, we calculate the length of the array n. Then, in step 1, we identify the longest non-decreasing prefix by initializing a pointer left at the start of the array. As long as the current element is less than or equal to the next element, we increment left. If left reaches the end of the array, it means the entire array is already sorted, and we can return 0 since no subarray needs to be removed. Next, in step 2, we find the longest non-decreasing suffix by initializing a pointer right at the end of the array and moving it backward while the elements remain in non-decreasing order. At this point, the initial result is calculated as the smaller value between removing the elements between the prefix and suffix or removing the suffix itself. To refine the result further, we attempt to merge the prefix and suffix in step 3. Two pointers, I and j, are initialized at the start of the prefix and the start of the suffix, respectively. While I does not exceed the end of the prefix and j has not yet traversed the entire suffix, we compare the elements at these indices. If the element at I is less than or equal to the element at j, it means the prefix and suffix can be merged at this point, so we update the result to the smaller value between its current value and the number of elements between I and j. Then, we move I forward to continue the comparison. If the condition is not met, we increment j to explore further into the suffix. Finally, the function returns the minimum result, which represents the length of the shortest subarray to remove. In this Java implementation, we start by importing the necessary utilities and defining the solution class. The main method here is findLength of shortest subarray, which takes an integer array ARR as input. The first step in solving this problem is to identify the longest non-decreasing prefix in the array. We initialize a variable left to 0 and increment it while the current element is less than or equal to the next one. This loop stops as soon as we find a decreasing pair or reach the end of the array. If left reaches the end, it means the array is already sorted, so there's no need to remove any subarray, and we can directly return 0. Next, we focus on finding the longest non-decreasing suffix. We initialize a variable right to the last index and decrement it while the current element is greater than or equal to the previous one. This helps locate the starting point of the suffix. At this point, we calculate an initial result by determining the minimum elements to remove to connect the prefix and suffix. This is done by comparing the length of the middle section between them with the size of the suffix itself. Now, we attempt to merge the identified prefix and suffix to minimize the size of the subarray that needs to be removed. We use two pointers, I starting at the beginning of the prefix and j at the start of the suffix. While I is within the prefix and j is within the suffix, we check whether the value at ARR, I, is less than or equal to the value at ARR, j. If it is, we calculate the potential result by removing the elements between these two indices and update the result with the minimum value. After this, we increment I to explore further into the prefix. If the condition is not met, we increment j to move further into the suffix. This way, we evaluate all possible overlaps between the prefix and suffix. Finally, after the loop completes, we return the result, which represents the length of the shortest subarray that can be removed to make the entire array sorted. In this example, we are given the array 1, 2, 3, 10, 4, 2, 3, 5. Our goal is to find the shortest subarray we can remove to make the entire array sorted in non-decreasing order. The first step is to identify the longest non-decreasing prefix. Starting with left equals 0, we compare adjacent elements. Since 1 equals 2, we increment left to 1. Next, 2 equals 3, so we increment left to 2. Then, 3 equals 10, so we increment left to 3. However, 10 equals 4 is false, so we stop here with left equals 3. This means the prefix 1, 2, 3, 10 is the longest non-decreasing sequence starting from the beginning. Next, we identify the longest non-decreasing suffix starting from the end. With right equals 7, we compare 3 equals 5 and decrement right to 6. Then, 2 equals 3, so we decrement right to 5. However, 4 equals 2 is false, so we stop with right equals 5. The suffix 2, 3, 5 is the longest non-decreasing sequence from the end. Removing the middle portion between left and right, we calculate the initial result as min, n left 1, right. Here, n equals 8, so the result is min, 8 to 3 1, 5 equals min, 4, 5 equals 4. Now, we try merging the prefix and suffix to potentially reduce the result further. Starting with I equals 0 at the beginning of the prefix and j equals 5 at the start of the suffix, we compare arr, I equals rr, j. Since 1 equals 2, the condition holds, so we update the result to min, result, j I 1. This gives min, 4, 5 to 0, 1 equals 4. We then increment I to 1 and compare 2 equals 2. Again, the condition holds, so we update the result to min, 4, 5 to 1, 1 equals 3. Next, we increment I to 2 and compare 3 equals 2, which is false. We increment j to 6 and compare 3 equals 3, which is true. Updating the result gives min, 3, 6 to 2, 1 equals 3, and we increment I to 3. Now, 10 equals 3 is false, so we increment j to 7. Finally, we check 10 equals 5, which is also false, and stop here. The final result remains 3, indicating that removing 3 elements will make the array sorted. In the second example, the input array is 1, 2, 3, 4, 5. Here, we start by finding the longest non-decreasing prefix. Since the entire array is already sorted, we can increment left until it reaches the last index, left equals 4. At this point, we check if the array is already sorted by verifying if left equals n1. Since this is true, no elements need to be removed. The array is already sorted, and the result is 0. For the third example, the array is 1, 3, 5, 4, 6, 7. First, we find the longest non-decreasing prefix. Starting with left equals 0, we increment left as long as the sequence is non-decreasing. This gives left equals 2, corresponding to the sequence 1, 3, 5. Next, we find the longest non-decreasing suffix starting from the end. Starting with right equals 5, we decrement right until the sequence 6, 7 is identified, giving right equals 3. To calculate the initial result, we remove the middle portion between left and right. With n equals 6, the result is min, 6 to 2, 1, 3 equals min, 3, 3 equals 3. Finally, we attempt to merge the prefix and suffix. Comparing elements between the two, we determine that removing the single element 4 is optimal. This updates the result to 1. Therefore, the shortest subarray to remove is of length 1, and the final result is 1. In analyzing the time complexity of this solution, we can break it down into 3 main steps. The first step is finding the longest non-decreasing prefix of the array. Here, we iterate from the start of the array until the condition of being non-decreasing breaks. Since this involves a single pass through the array, it requires at most n time, where n is the length of the array. Next, we focus on finding the longest non-decreasing suffix, which operates similarly but starts from the end of the array and iterates backward. This also takes at most n time. The final step is merging the prefix and suffix to determine if they can form a valid sorted array. Using 2 pointers, we iterate over the prefix and suffix to find a valid merge point. In the worst case, the pointer traversing this suffix may run through all its elements, leading to another O(n) operation. Altogether, each of these steps contributes linearly to the overall complexity. When we sum up the contributions from each step of the algorithm, we get a total time complexity of O(n) plus O(n) plus O(n), which simplifies to O(n). Now, let's look at the space complexity. This algorithm is highly space efficient because it uses only a small number of integer variables to store indices and intermediate results, such as n, left, right, I, j, and result. Importantly, it does not make use of any additional data structures like arrays or hash tables. Since the space needed does not grow with the size of the input array, the space complexity is constant, or O(1). This combination of linear time complexity and constant space complexity makes the solution both fast and memory efficient. To better understand the performance of this algorithm, let's analyze it across best, average, and worst-case scenarios. In the best case, the array is already sorted, either entirely non-decreasing or non-increasing. Here, the prefix spans the entire array, so the algorithm terminates early with a result of 0, requiring only O(n) time. In the average case, the array contains a mix of sorted and unsorted segments. The algorithm performs all three steps, but the prefix and suffix help reduce the search space for merging, leading to an expected time complexity of O(n). In the worst case, the array is completely unsorted, with no overlap between the prefix and suffix. Even in this scenario, the algorithm fully executes its steps, and the complexity remains O(n). To put this into perspective, a brute force approach would check all possible subarrays to find the shortest one that results in a sorted array, leading to a time complexity of O(n cubed). In contrast, the optimized solution leverages the properties of non-decreasing subarrays and efficiently merges them using two pointers, significantly reducing the complexity to O(n). To solidify our understanding, let's consider a mathematical proof of the big O complexity. Each loop in the algorithm runs independently and iterates at most n times. Since there are no nested loops, the operations combine linearly, resulting in an overall time complexity of O(n). On the space front, the solution avoids using additional data structures, relying only on a fixed number of variables for computation. This ensures that space usage remains constant, or O(1). In conclusion, the algorithm is optimized for performance, achieving O(n) time an O(1) space complexity. This makes it a significant improvement over brute force methods, providing both speed and efficiency in solving the problem. When tackling this problem, there are a few common mistakes to watch for. First, not considering edge cases with fully sorted arrays can lead to errors. If the array is already sorted, the shortest subarray to remove is of length 0. Failing to check for this upfront might result in incorrect outputs or even runtime errors. The solution is to always verify if the array is non-decreasing at the start to save unnecessary computations. Another mistake is assuming the subarray to remove must be contiguous. While the removed section itself is contiguous, the two remaining parts of the array only need to merge into a sorted sequence. This misunderstanding can lead to overly complex or incorrect logic. Finally, a common pitfall is relying on a brute force approach, where you iterate over all possible subarrays to check if the remaining parts are sorted. This has a time complexity of O(n cubed, which is impractical for large inputs. A better strategy involves using techniques like two pointers or binary search to reduce the complexity to O(n), or O(n log n). Now, another crucial point is properly merging the left and right segments. If you fail to merge the sorted prefix and suffix correctly, you might miss valid solutions. The key is to find the longest valid prefix and suffix, and then determine the overlap using efficient techniques like binary search or two pointers. Additionally, it's important to account for duplicate values in the array. If your comparisons are not inclusive, such as using greater than instead of greater than or equal to, duplicate values can break your logic. To address this, ensure your comparisons are inclusive so that equality is properly handled when working with non-decreasing arrays. For interviews, this problem is an excellent opportunity to demonstrate your understanding of key patterns and optimization strategies. The core idea involves finding the longest sorted prefix and suffix, and then minimizing the gap between them. This approach is a common pattern in array segmentation problems. It's also important to emphasize optimization thinking. Use techniques like sliding windows or binary search to reduce time complexity, and be ready to discuss the trade-offs between simplicity, as seen in the two-pointer method, and performance, as seen in binary search. Always highlight edge cases during interviews, such as empty arrays, single-element arrays, or arrays that are already sorted, as it demonstrates thorough problem analysis. Additionally, you should be prepared to explain why brute force is inefficient and how optimized solutions take advantage of the array structure to achieve better performance. This problem has some interesting connections to related LeetCode problems. For instance, LeetCode number 581, the shortest unsorted continuous subarray, also involves identifying the smallest range to modify for sorting. Similarly, LeetCode number 42, trapping rainwater, uses left and right pointers to solve efficiently, which aligns with the two-pointer technique here. LeetCode number 11, container with most water, is another example of a two-pointer problem where you need to optimize merging conditions. Lastly, LeetCode number 209, minimum size subarray sum, focuses on minimizing subarray length, which parallels the goal of this problem. Among the alternative approaches, the two-pointer method stands out. Here, you identify the longest sorted prefix and suffix, then minimize the gap between them. This approach runs in O(n) time, making it both efficient and simple to implement. However, it does require careful handling of edge cases. Another efficient approach is binary search. This method involves combining a sorted prefix with a position found via binary search in the suffix. It has a time complexity of O(n) log n, making it suitable for larger arrays. While it is more efficient than the two-pointer approach for certain inputs, it is also slightly more complex to implement. On the other hand, the brute force approach, which checks all possible subarray removals to see if the remaining parts are sorted, is straightforward and easy to understand for small inputs. However, its O(n) cubed time complexity makes it impractical for larger arrays. For optimal solutions, focus on the two-pointer or binary search approaches, both of which strike a balance between efficiency and clarity. Great work! We've successfully covered LeetCode problem number 1574 and discussed key insights into solving it efficiently. Remember, mastering techniques like two-pointers and breaking problems down into manageable steps is crucial for improving your problem-solving skills. Thanks for watching, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!